Before starting, before I'd like to apologize. This is a very, very important day for not only Yuki, but for me as well. But unfortunately, I just came back from CES and I got COVID-19. I've been getting all my vaccination shots. I missed just one shot, the latest one, and this is what happened. So I highly encourage everyone to get updated with your vaccination shots. Again, thanks for everyone for coming for Yuki Shirai's PhD defense. It's a delight to introduce Yuki. I'm sure that you already know Yuki. Yuki, you've been with us for 6 years, almost 6 years.
Yeah,
right?
five years, more than 5 years. Yeah.
Yeah, 5.5 years or something like that. He did his undergraduate at Toku University in Japan. He's been working on many projects, so mainly for planning with contact, locomotion, manipulation, and he's done so much great work as his publication list really shows. How many journals papers do we have, including under review? We have quite a bit, right?
Like 4, 5, like that.
Okay, yeah, but he has a pretty good, very, very high quality publication list. During the past 5-6 years, he's been also active doing research interns. Twice he was intern at the Mitsubishi Electric Research Laboratory, and the latest he was at the Boston Dynamics AI Institute. So Yuki is not only a fantastic researcher, but he's a great person. And as a person, he's really fun to work with and very polite. So I'm very glad and sad. If he passes, I'm sad that he's going to be leaving us as well. So today, Yuki's going to be presenting his work in a very, you have to really make it short. Don't go over an hour. I think we're planning for 55 minutes presentation.
Yeah.
Yuki's going to be talking about 3 topics mainly. His work on planning through contact for free climbing using his computationally efficient framework. And second, robust planning through contact with his novel optimization algorithm. And third, this closed-loop control for tool manipulation, but only using joint encoders and tactile sensors. So without any further ado, I'll let Yuki take the stage. Yuki.
Yeah, thanks, Dr. Hong, for your kind introduction. And thanks for everybody to come to my PhD defense presentation. I'm very happy to have my presentation today. Today, as you can see in these teaser videos, I would like to talk about planning and control framework, which I have been working on last 5 years, especially focusing on climbing robot or walking robot or tool manipulation, as you can see here. I mean, although I'm gonna mainly talk about 3 projects, which Dr. Hong just described, the key message I would like to talk about or convey is considering contact is critically important to introduce dexterity of locomotion manipulation. But considering contact makes design of planning, estimation, and control for robotic system quite extremely challenging. So I hope I can show some examples how we solve planning, control, and estimation. And hopefully you guys can learn something from this presentation. Okay. So let me first get started with the motivation. So nowadays robotic manipulation has shown impressive results. For example, as you can see here, robotic manipulation has been used for some simple tasks such as pick and price in highly structured environments such as factories. Also, nowadays, robots such as Spot from Boston Dynamics has shown remarkable capability in locomotion tasks such as monitoring, delivery, and inspection. Although those robots have shown impressive results, I would say the current manipulation and locomotion algorithms are still very inefficient in performance. For example, for this robotic manipulation, it can do very great work in kind of simple tasks, pick and place, but in highly structured environments, such as factories, where planner, estimator, controller, everything are guaranteed to success. I think we want to do a bit more. In fact, we humans can achieve very dexterous tasks through contact, even under uncertainty. So here I'm showing one example for bimanual assembly for toolbox, for a gearbox. Here he understands which arm he gonna use, which arm he tries to grasp tool, how much force he needs to apply, what kind of motion he needs to apply to the system to assemble the gearbox, which is very, very contact-rich task, I would say. Similarly, we humans can do I cannot do free climbing, but some people can do free climbing task. where he can understand when to make contact, when to break contact, how much force he needs to apply to the environment to accomplish climbing task. What I'm trying to say here is just doing, we human can do very, very complex tasks through contact. And my research motivation during my PhD is, can we make robots perform very dexterous tasks as we human can do? That's the research motivation. But of course, there are many challenges, right? First, planning through contact is already quite challenging. In planning without considering contact, where contact mode sequence, such as when to make contact, when to lose contact, those information is fixed. It's given by users. And optimizer is able to just focus on designing a continuous trajectory of the robot, such as the leg trajectory or body trajectory of the robot. As a result, optimizer can potentially find a solution efficiently. However, since optimizer does not consider the change of contact, the generated trajectory, planned trajectory from the optimizer might not be physically feasible. And thus robot just fail to climb for this specific demo. In contrast, in planning through contact, now contact mode sequence, such as when to make contact, when to break contact, is not given by users. And thus optimizer needs to figure out what's the right appropriate contact sequence to complete its desired task. Okay, if somehow optimizer can figure out the optimal contact sequence, maybe if we command trajectory on the hardware, since now optimizer could successfully consider the appropriate contact dynamics, robot can successfully achieve climbing task for this specific demo. Of course, there are some challenges. The key challenge is, in order to make optimizer consider the change of contact, you often consider like mixed integer constraints or complementarity constraints if you use trajectory optimization framework. That dramatically increase the computational complexity once you have too many contacts. So the key question is how to deal with those complicated constraints, even if you have many contacts. Another challenge arises from uncertainty, right? In reality, uncertainty always exists, such as mass, friction of the object during manipulation. Here we want to do pivoting manipulation, where we want to reorient object by 90 degrees. But since we couldn't do good system identification of the coefficient of friction between the object and the environment, the object loses contact. Similarly, again, because we couldn't do good system ID, robot lose contact. Here we are trying to do pushing manipulation, where we want to bring the object from start state to goal state. However, even though we use very, very good robot manipulator with very, very good position control accuracy, still robot could not, bring the object to its desired state, because we have very, very complicated friction dynamics between the object and the environment. So the key question is, how can we design robust optimization such that the designed trajectory will be robust against physical parameters such as mass, friction, stuff like that? What's more, once you have too much uncertainty, maybe just using robust optimization might not be enough. And thus closed-loop controller will be very, very beneficial. However, designing of closed-loop controller for contact-rich system is in general very challenging. Here, we showcase our closed-loop controller for tool manipulation task. Okay, we don't use any vision sensors, so we don't know the pose, we cannot estimate pose of the object. However, even if we use vision sensors, right, in order to do closed-loop control, you still want to guess if contact is sticking or slipping. You also want to know how much force is happening at each contact state to regulate the whole tool manipulation task. So the key question is, how to estimate those contact states for this kind of complicated contact system. Okay, although, so with those motivations, through my PhD, I have been focusing on those two axes. So the y-axis or vertical axis considers if my framework consider open loop control or closed loop control. When I say closed loop control, it means like MPC, model predictive control. My framework use sensor measurement to replan the trajectory. In open loop, I don't replan trajectory. X-axis consider if the framework consider hybrid contact dynamics or no. So when I say hybrid contact dynamics means if the framework allow the system to change contact mode or not. In other words, in continuous dynamics, I assume contact mode sequence is fixed during locomotion and manipulation. Okay, based on those two axes, I can categorize my previous works into 4 sub-blocks. For example, I have been working on some chance constraint optimization for vertical wall climbing robot. I also did some tool manipulation work for closed loop control. Nowadays, I've been focusing on more like hybrid optimization, considering like robustness or performance for very contact-rich tasks. Today, I don't have time to talk about one of the stochastic optimization projects I did during my PhD, but if you are interested in, I'm very happy to talk offline. We did some stochastic optimization for designing like feed forward and feedback gain for contact-rich system under chance constraint. But today I would like to focus on those 3 projects. First, I'm gonna talk about our proposed like, distributed optimization technique so that robot can efficiently design trajectory with multiple complicated contact constraints. Second, I'm gonna talk about our novel Bilevel contact-implicit trajectory optimization, which can design optimal controller for pivoting manipulation, as you can see, while simultaneously optimizing the worst case stability margin during pivoting, so that robot can do very, very robust manipulation. And finally, I'm gonna talk about our closed loop controller using visual tactile sensor, which is GelSlim. Okay. So let me get started with the first chapter of this dissertation, which is planning through contact. So just for recap, Electro Robot has shown impressive results. What I'm trying to say here is we want to do a bit more. So let's see. In order to accomplish those like more complicated tasks, which traditional Electro Robot cannot accomplish, we need to additionally consider like, those complicated constraints. In this experiment, in this chapter, actually, we're gonna focus on free climbing task. Although all the algorithm I'm gonna talk about today can be applied to other locomotion and manipulation tasks. But here I'm gonna use our algorithm for free climbing task because this is challenging project, challenging application. So first, why this problem is challenging? Why designing trajectory for this free climbing robot is challenging? If you use trajectory optimization, you're gonna have like many different complicated constraints. For example, you need to consider dynamics, kinematics, constraints of the robot, which would be nonlinear constraints because you have a bunch of sine, cosine stuff, right? Because for this free climbing task, it's not trivial. What's the right optimal contact sequence before we do climbing? So we ideally want to optimize that to figure out what's the right optimal contact sequence, which makes optimizer use integer constraints to consider those discrete decision making. Another challenge arises from scale of the optimization problem, right? We are our lab has been working on Electro Robot, but this is like not like traditional Electro Robot, right? We have 4 legs where each leg consists of 6 DOF. So we need to consider position and orientation of the end effector. And each leg consists of like 2-finger gripper. So that also introduces additional dexterity or complexity. Also, the environment is not like flat terrain, right? Environment consists of those like boxes in order for the robots to grasping for climbing. That also introduces additional complexity. So optimization problem is very large scale with many integer constraints. So how to design trajectory efficiently? Okay, so the problem statement is as follows. We want to design optimal, let me see how much, okay. We want to design optimal trajectory of finger and body pose, contact range, and contact sequence simultaneously. And we have some assumptions. For example, we have the robot is equipped with 2-finger gripper, although we can consider 3-finger gripper, 4-finger gripper. that will just increase complexity of the problem. And we assume that the environment consists of rigid and static convex holes. So we don't assume that those convex holes will move during locomotion. Okay, so let me actually describe our problem formulation. So this is our trajectory optimization. So we have a bunch of decision variables. X is for state of the system. U is control input for the robot. We have Z, which indicates integer variable. And for each time step, you need to consider like many different complicated constraints, right? So first, we need to consider dynamics of the robot. I mean, this is basically Newton's second equation, right? F equal ma. So we consider linear dynamics and angular dynamics of the robot to maintain stability of the robot. We consider contact force, contact moment, I mean, body position, finger position to formulate these dynamics constraints. Angular velocity of the body, I don't think I need to explain this part because I think everybody knows Newton's equation. And for each finger, we actually need to bound the range of the finger to move, right? You cannot place end effector to anywhere, right? There should be some range where you can place your end effector. So we have some constraints to prevent end effector from, going to outside of the workspace, which would be function of body and finger pose, which is gonna be also formulated as nonlinear continuous constraints. And for each finger, we want to discuss if the contact is making or breaking. And this will require using integer variable. In particular, we use BQM formulation to discuss if the contact is making or breaking using integer variable. And for each contact, we consider that force follows our proposed limit surface model. Because we work on free climbing, we had to use some sophisticated contact model so that robot can ensure stable climbing task. I mean, I don't explain this part in detail. You can think we have some like specific contact model to ensure sticking contact for climbing. And we also have to consider collision avoidance constraints. This is kind of a unique constraint for this free climbing task because for traditional locomotion problem, I think you don't need to explicitly consider the collision constraints because we assume environment is flat. However, as I showed, for climbing, we have environment where we have multiple like climbing holds in order for the robot to grasp to accomplish climbing task. If we don't consider this constraint, robot can design trajectory such that finger or body can penetrate into the climbing objects, climbing holds. So we have to explicitly consider collision avoidance constraints, which also introduce, integer variables. So this is the optimization problem we are interested in working on. But this optimization problem is challenging, right? We have a bunch of nonlinear and integer constraints. So what we did was we basically utilized ADMM to decompose optimization problem into two optimization problems. The key idea is divide and conquer. So what I'm gonna say is, instead of solving original large-scale MI-NLP problem, we have MIQP, mixed integer quadratic programming, and NLP to solve sub-optimization problem. Okay, how about this? So I bring all the integer constraints from MI-NLP to MIQP, and I bring all the continuous constraints into NLP, and I solve each optimization problem separately, right? So if you solve optimization problem separately, you're gonna have this kind of optimization problem, and you're gonna get solution X star and Y star from MIQP and NLP respectively. Ideally, if X star is equivalent to Y star, what does it mean? If X star and Y star, if those two solutions are identical, it means the solution X star and Y star satisfy all constraints from MIQP and NLP. This is a very important part I want to talk about in the first part. So do you see? So if you can, if X star and Y star equal, we satisfy all the constraints from MIQP and NLP, which means we indirectly solve the original MI-NLP problem. So that's what we did. So more detail is we first solve MIQP and NLP with some soft consensus constraints. So we have some term in the cost function for MIQP and NLP to encourage those two optimization problems give me the similar solution or ideally same solution. And we calculate the residual of those two solutions. And we keep repeating this process again and again until those two optimization give me similar or ideally same solution. There are several advantages, right? First, we don't need to work on MINLP. That's good. We can use off-the-shelf solver such as Groby for MIQP, IPOpt, SNOpt for NLP. So they are very powerful optimization solver, so that's very good. Also now optimization problem scale is decreasing, right? Now we don't need to work on one big optimization problem. So numerical stability improves. Okay, so those are some advantages. So I'm gonna show some results. First, I'm gonna show some computation results. So I use Groby and NLP, so Groby and IPOpt for optimization solver. And we use our robot scaler for testing in hardware experiments. So first, let me show our results for climbing and walking task. Here I compare our algorithm with respect to benchmark method. So when I say benchmark, we convert the original MI-NLP problem into NLP problem by converting all integer constraints into complementary constraint. And I just use IPOpt for benchmark optimization. And as you can see, for both computation time and success rate, our algorithm outperforms in both computation time and success rate for walking and climbing task. And this is some results of the climbing task. As you can see, because we could successfully consider, all those complicated constraints, robot can successfully achieve climbing task.
Successfully, that you get consensus.
Consensus in optimization. Yeah, that's true. I mean, even though we achieve consensus, it doesn't necessarily mean hardware experiment works. That's true. But when I say success means optimizer converge. And fortunately for this specific demo, hardware experiment also works. Yeah. So this is a case where we have the obstacles. So you can think those yellow boxes are representing obstacles. In our setting, optimizer think the height of obstacle A is low. Robot just steps over the obstacle. However, in contrast, in object B, optimizer thinks the height of the object B is high. Robot takes detour. It doesn't take step over. It takes like detour to avoid collision. And you can observe this kind of rich trajectory, like different trajectory by considering kinematics or collision, contact simultaneously. This is the final video where we consider the object and climbing hold where orientation is different. And we have high friction phase and low friction phase for climbing hold. Since our optimizer can think, kinematics, friction simultaneously, in order to ensure grasping on high friction phase, robot changes its end effector orientation to ensure grasping in high friction phase. Okay, that's the first chapter of my presentation. So
May I ask a question?
Yeah.
So in the previous experiment that you showed, is the environment well defined and all the optimization is done offline or it's done online? And,
sounds good.
And in case something will go wrong, meaning something will slip, how the system would perceive it and adapt for it?
That's a great point. Thanks. So to answer your question, so first, this one, everything, all the computation happen offline. We exactly know the environment. We know how much friction we have on the environment. We know orientation and position of the climbing hold location. We know everything exactly beforehand. And during hardware experiment, yes, if there's some mismatch happen, robot fail. But the thing is, this is open loop control, and we did not discuss any robustness. So actually, this experiment can be fragile if we don't start robot in the exactly correct location at t equals 0. So because we don't do any feedback. I mean, we do feedback in motor, but we don't do any MPC style feedback. So yes, if we don't place the robot on the very, very accurate position at t equals 0, this experiment doesn't work.
And any error that you will generate over time may build up to lead to a much bigger error that will eventually lead to a failure, right?
Yeah, that's I think absolutely correct. So in fact, even though we show some multiple step climbing, we didn't show like 10 steps or 20 steps or 100 steps climbing, right? Because as you just described, eventually error will be accumulated. Because the main focus of this project was more like computational complexity part. We want to show, oh, we have some cool framework which can design trajectory efficiently. I mean, although I show some hardware experiment results, I would say this is not kind of main focus. Our main focus is more computational complexity. And in order for hardware experiments to work pretty well, we need to have more robust optimization and closed loop control, which I'm gonna talk about soon. But that's a great point. Yes, we didn't show multiple step climbing. Yeah. Okay. So let me move on to like robust planning part. So here I would like to motivate a bit about why pivoting manipulation is fun or challenging. So here we want to do like assembly task where the object might be too large for the gripper to grasp, and thus robot might not be able to grasp, right? Similarly, if the peg is undesired pose, not desired pose, robot cannot grasp with the good configuration, and thus robot fail to insert. So our motivation is, can we first reorient parts and thus robot can grasp? So in other words, we first do pivoting and then we can do grasping. But in order to do pivoting, we need to consider many things. There are many challenges. First, in grasping, we consider sticking contact, where eventually you just increase grasping force as hard as possible. Then you can robustify manipulation, right? If you increase your normal force of the finger, you can have very good grasping manipulation. In contrast, in slipping control, for pivoting manipulation, we need to consider slipping contact, where increasing normal force doesn't mean we introduce more robustness, right? If you don't know this cone represents friction cone constraints. This cone is basically saying if contact force is within this triangle, contact does not slip. Otherwise, it slips. So in slipping control, we need to actually make friction force on the edge of the friction cone, which is very challenging because this is equality constraints. Bringing force to equality constraints is very challenging, right? You need to simultaneously increase normal force and shared force together, right? To ensure force is on the edge of the friction cone. This actually makes the robust optimization find solution much more difficult. So in traditional robust optimization, our goal is we want to find optimal control input U to satisfy, inequality constraints for all realization of uncertainty. But here, because of this slipping contact, which is equality constraints, we cannot find optimal control input U to satisfy all uncertainty realization. We cannot do robust optimization with equality constraint, right? You have object whose mass is 10 kilogram, 8 kilogram, 100 gram. You cannot find control input U, which is gonna work for all different realization of uncertainty with this slipping contact. What's more, during manipulation, we observe that just, if the robot contact does not move, robot cannot complete its pivoting task. And thus we realize that actively controlling contact location is critically important. And to do that, we need to consider sticking, slipping, hybrid contact dynamics so that robot can change contact state from sticking to slipping and vice versa, which can be realized by considering complementarity constraints. There are many great related works. Those work achieve some deterministic planning with sticking contact. Some work from CMU and MIT did some great like slipping contact manipulation. Those work could achieve some like locomotion with some robust optimization. And what we are proposing is we can do robust planning with slipping contact. Okay. So the problem statement is as follows. So we want to design open loop controller for pivoting manipulation with 2 extrinsic contact and 1 contact from a robot. And we can formulate trajectory optimization problem like this nonlinear programming with complementarity constraints. where we have X, U, F as state control input and extrinsic contact force decision variable. So we consider object angle, finger contact location, contact force from the robot to the object, and extrinsic contact force as decision variable. So by solving this optimization problem, you can find optimal control input. But I didn't talk about how to incorporate robustness, which I'm gonna talk about. So the key insight is friction can compensate for uncertainty. That's the key message I want to talk about in this chapter. So let's consider the case where mass, weight of the object is lighter than what you estimated. If the weight is lighter than what you estimated, friction forces can adjust to maintain stability of the object. Okay, if you command the robot for pivoting manipulation, even though you don't change anything, right? Even though you use incorrect parameter of the friction, to some extent, robot can still achieve pivoting manipulation because friction can take into account, friction can compensate for that noise, uncertainty. Similarly, if the weight of the object is heavier than what you estimated, again, to some extent, friction forces can adjust to maintain stability of the object. So we call this range where friction can still compensate for uncertainty as frictional stability margin. As you can imagine, this frictional stability margin should change along trajectory. Right? This stability margin is a function of the trajectory of the robot, object, and contact forces. So what we are interested in is we want to design controller which can improve this stability margin. Okay, so we have the time history of the stability margin. So this x-axis represents time and y-axis represents stability margin. And we want to know the upper bound and lower bound of the stability margin to do some robust optimization. And in order to know upper bound and lower bound of the stability margin, we use linear programming to get the upper bound and lower bound. Once you get time history of the stability margin, you can solve another optimization problem to design open loop controller, which can improve the worst case stability margin. I basically did some min-max optimization, right, to improve the worst case stability margin. Okay, once we solve the right optimization problem, now you're gonna have the new control input, right? Because we want to improve the worst case, we design optimization problem such that it's gonna improve the worst case stability margin. So that means now you have a new trajectory, and stability margin is a function of the trajectory of the robot, object, and contact forces. Now stability margin should also be updated because now trajectory from the robot is different. And we can keep iteratively solving those two optimization problems again and again until we're gonna have a better controller. But can we do a bit better? Can we simultaneously optimize those two optimization problems together for better optimality? And we can do Bilevel optimization problem. So what we did was in order to simultaneously solve those two optimization problems, I make this optimization problem as lower level optimization problem and finding optimal control problem as upper level optimization problem, which can be formulated as follows. In general, finding solution for robust optimization, in general, finding solution for Bilevel optimization is quite complicated, quite challenging. But we intentionally formulate the lower level optimization problem as convex linear programming. We can use KKT condition to convert all the lower level optimization problem into bunch of linear and complementarity constraints. So what I'm trying to say here is eventually I solve one single stage large scale NLP with complementarity constraint, which can be efficiently, solved through IP-opt or SN-opt. Okay, so I think I'm talking about too much detail, but what I'm trying to say here is I basically propose some framework which can do pivoting manipulation, but we can do a bit better. So even though we guess the weight of the object is 100 grams, our optimizer can also give me 70 grams and 160 grams as solution, as output of the framework. And it says, hey, Yuki, you can still successfully achieve pivoting manipulation as long as the true mass of this gear is within this 70 and 160 grams. And those numbers output of our algorithm. Okay, so we did some experiments in hardware. I'm gonna first show some robustness experiments. So we intentionally use incorrect parameter as input of optimization problem. So here, I assume the mass of this blue gear is 100 grams, although the true mass is 140 grams. If the framework is really robust, it means we can still achieve pivoting manipulation, right? And this is the result. So here, benchmark is a method where we don't consider frictional stability margin, just traditional project optimization problem. If we use our optimization problem for each different incorrect mass parameter, we can do pivoting manipulation. And this is some results of hardware experiments. Okay. So we can do pivoting for different objects, as you can see here. Since our algorithm is general, we can do pivoting manipulation for different objects, as you can see here. Okay. So far, okay, what's the limitation of this work? We did not consider the case where object shape is non-convex. So something like this peg. Why we don't consider this kind of object? The reason is that now contact location can change during manipulation. So for this peg, right, until t equals t1, contact is always happening at those orange dots, right? However, after t equals t1, now contact location will be on those green dots. So that means contact mode change. So contact location change before and after t equals t1. Why this is challenging? Why this is challenging? Yeah. The thing is, remember, when we solve lower level optimization problem, we use linear programming and we can use KKT condition to get upper bound and lower bound of the stability margin as shown in those orange lines. However, now in order to consider the change of contact mode in lower level optimization problem, one way we can do is we can use complementarity constraints. But using complementarity constraint in lower level optimization problem means now the lower level optimization problem becomes non-convex optimization problem due to complementarity constraint. So if we have non-convexity in the lower level optimization problem, KKT doesn't give you globally optimal solution, right? Now KKT might give you some potentially locally optimal range. For example, as you can see those blue lines. So it doesn't give me orange lines anymore. It just gives me some blue lines. And if we design controller using those blue lines, the controller would be very, very suboptimal, which we want to avoid. So what we did was, okay, let's give up doing stability margin optimization over contact mode. But can we at least optimize with contact mode duration? How much each contact mode spend? Can we optimize at least contact mode duration? That's what we did. So we identify, so one assumption is we still know contact mode 1 happens at orange. We at least assume that contact mode sequence is given. But first, we're gonna identify what kind of constraints are used for each contact mode respectively. So we need to identify F1 is for contact mode 1, F2 are used for contact mode 2. However, now we want to optimize not only X, U, F, but also T to optimize contact mode duration. Now you have this kind of if function with the function of decision variable, which we want to avoid. So what we did was we basically did normalization. So what I'm saying here is just divide it. Let's divide theta dot object angular velocity and fingertip velocity with T1 and T2. What does it mean? So it basically now does, if you focus on that sentence, so if function doesn't have decision variable anymore. So in other words, by doing normalization by the decision variable, now we can guarantee that switching timing is always at t equals 1 second. So previously, we don't know when contact mode switch because T1 and T2 are decision variable. But by doing this normalization, I would say this kind of technique has been used in optimization community for many years. So I just utilized that technique. But by doing normalization, now we know exactly at t equals T1, so at t equals 1 second, contact mode switch. And we can do now robust optimization for this kind of peg. So this is my favorite video, but now if you know this peg is actually heavy. And this peg is the geometry of this peg is super non-convex. But still, our optimizer is able to design robust trajectory, and in practice, in hardware experiments, it works well. Okay, so that's the second part of my presentation. Then I'm gonna talk about my final part. Okay, so again, let me briefly motivate why tool manipulation is challenging. Okay, for traditional grasping problem, we can often assume that robot is making 2-point contact. Okay, let's use if you use like 3-finger or 4-finger gripper, maybe number of contact increase. But at least manipulator can directly grasp object. That's very good. Also, this is inherently stable. Again, robot can increase normal force at fingertip to robustify manipulation. In tool manipulation, on the other hand, now you have multiple contacts. That makes the design of planner estimator controller quite challenging. Also, this is manipulation for one object using another object, right? So you cannot just directly manipulate this yellow mustard bottle. You need, in order to interact with yellow mustard bottle, you first need to use another two object, which is tool, to manipulate the yellow mustard bottle, which introduces more complexity. This is inherently unstable manipulation, right? We don't know what's the right direction for robot to move the tool to stabilize manipulation. So that's quite a challenging problem. Okay. So mechanics is already quite complicated, and contact estimation is also very challenging, as I mentioned in the beginning of this presentation. Okay, so there are many great works in this field. Those work achieve some open loop tool manipulation. Those work, especially from Alberto's group at MIT, has shown impressive results in using force and visual tactile sensing. And our work can also do closed loop control using visual tactile sensing for tool manipulation. So let me briefly explain the contribution here. First, we're gonna identify the contact mechanics for tool manipulation, which provides the constraints with motion planner to simultaneously design end effector, tool, and object trajectory. Using this trajectory computed offline, we do closed loop control. So under unexpected contact events, visual tactile sensor is able to detect slipping. And using this slipping information, our proposed tactile estimator is able to estimate the pose of the object and tool simultaneously. And using this estimate, our MPC-based controller is able to track the reference trajectory. Okay. So let me first briefly explain mechanics. So we want to do pivoting again using external tool. And we have some assumptions. For example, we assume that the object and the environment are rigid. We also assume dynamics is quasi-static, so no acceleration. We don't consider acceleration. Also, we assume that the kinematics geometry of the tool is known. We also assume friction coefficients are known. We consider manipulation in 2D, as you can see here. So we don't consider 3D manipulation directly. So those are assumptions I have in this work. In other words, I do not assume that the following parameters are known. So I don't know the length of the object. I don't know the global contact location of the object. I also don't know the angle of the object and actually tool. So we don't know those parameters. So our framework wants to do closed loop control while simultaneously estimating those parameters, which would become object agnostic manipulation framework. Okay. Okay, so now I'm gonna talk about mechanics. So I have to consider some constraints to achieve tool manipulation. So we consider like force equilibrium, force and moment equilibrium of object and tool. We also consider friction constraints to ensure sticking contact at each different contact location. Also, we consider force controller constraint. This is kind of unique constraint for this tool manipulation work. So initially, without considering this constraint. Optimizer just design trajectory with contact force, as you can see in the slide. Actually, when we command this trajectory in the hardware, robot could not complete a tool manipulation task. Because this friction force is not, the motion of this force is not constrained. What I mean is, in order to get reaction force, right? This is very basic part, but in order to get friction force, your motion needs to be constrained, right? If you want to get this reaction force along this axis, motion along this axis needs to be constrained. This is very basic part, but once the problem becomes very complicated, you need to explicitly consider this kind of detailed constraints. So in fact, what we did was we ensure that the force will be, the motion associated with force will be bounded or constrained, so that force will be physically generated. Okay, so that's the mechanics. Let's see how much I saw 43 minutes. Okay. So for planning part, this is not so complicated. We just use the nonlinear optimization problem. With where we have object angle, tool angle, and end effector angle as state. And we just use IP-opt to find solutions. That's it. Okay. So finally, I'm gonna talk about our framework for closed loop control. In order to do closed loop, you need to have controller and estimator, right? For controller, we didn't do any fancy stuff. So we just use the optimization problem I just described in the previous slide in receding horizon fashion. That's it. So the key challenge arises from the estimator part. So again, we want to estimate the following parameters: contact location of the object, length of the object, and current angle of the object, right? How to do that? We don't do Kalman filter, stuff like that. The key strategy is we can use two equations representing the same location and do least square. So this is very simple idea, but it works pretty well in hardware experiments. So what I'm trying to say here is, okay, let's use forward kinematics. So we want to represent contact location PB using homogeneous transformation matrices. So from world frame to frame A, and from frame A to frame B, we can use this kind of homogeneous transformation matrices, which are function of unknown parameters we want to estimate. Similarly, we can represent point PB using forward kinematics, which are function of sensor measurement from joint encoders and visual tactile sensor, which are attached to finger chip. Now we have two equations representing the same location. So we can do least square to get estimation of those parameters. That's it. I actually skipped one detail in the previous slide, which is how to convert visual tactile sensing information to get, how to get relative angle between the end effector and tool, which I'm gonna briefly talk about now. So in this project, we use GelSlim from MIT, where GelSlim is covered with deformable skin with many black markers. And what I did was, okay, by getting bunch of tactile images, right, you can actually compute optical flow, or you can actually get deformation, how much each marker moves, okay? And once you know how much each marker moves, and I use some vision sensor to get ground truth of the angle of the object, angle of the tool with respect to the end effector. And I just did a polynomial fitting, so that's it. So I mean, this is training phase. So okay, in hardware experiments, in actual implementation, we didn't use April tag. I'm just saying we did this kind of training to train some module so that visual tactile sensor information can be converted into relative angle between the object, between the tool and the end effector. Okay. Okay, so now I'm gonna show experiments. So we use, let me first show, okay, the results of open loop controller. So no feedback, just open loop. But since our optimizer thinks all the complicated constraints, it can design trajectory for this kind of complicated tool manipulation. And since our algorithm is general, we can do tool manipulation for different object tool pairs on different contact surfaces, as you can see. But of course, there are some cases where open loop fail. So first, sometimes tool can miss the contact at t equals 0. Okay. Also, we observe that tool can rotate in gripper, and thus robot eventually lose contact. I mean, the tool eventually lose contact with respect to the object. Okay. Also, if I add some disturbances, of course, unfortunately, it does not work. So now I want to show some closed loop control results. So now I'm showing open loop control and closed loop control results for pivoting manipulation. As you can see, while open loop controller lose contact during manipulation, in closed loop control, it could maintain contact and it could successfully achieve pivoting manipulation. Here I'm showing time history of the error of object angle. So here I'm showing time history of the estimation of the object angle in open loop and closed loop. So I added noise at t equals 40 seconds. And as you can see in closed loop control, since it's doing closed loop, it can react, it can respond to the sensor measurement, and it can still maintain the stability of the object. And thus, some of the assumptions of the tactile estimator are still maintained. In contrast, in open loop, it doesn't do any feedback, right? So as time goes, noise will be accumulated, and eventually robot lose contact and the tactile estimator diverged. Okay. So this is a final video I want to show. So here I added random noises during manipulation, and you can see we can still achieve closed loop control. The bottom left one I'm showing here is the result for regulation task, not tracking. So we want to regulate this triangle object along this red line, but still it can do closed loop control. Okay, so that's it. So finally, I would like to conclude this presentation with some key takeaways. So first, planning through contact is very challenging, especially in terms of computational complexity. It's very challenging, but I think distributed optimization techniques such as ADM would be useful to achieve better computational complexity. Second, incorporating robustness is very, very useful. I mean, very, very important, to achieve robust manipulation, especially with extrinsic contact. And I think I showed understanding contact mechanics is very important. I mean, if you don't understand the underlying mechanics, how can you robustify manipulation? That's my message. So I want to understand the underlying contact mechanics. And in particular, I propose some model-based optimization which can achieve robust manipulation efficiently and intuitively. I didn't show computation results, but at most it took like 2 minutes for finding Bilevel optimization solution. That's not that bad, I would say. And since we understand the underlying contact mechanics, we know why it works, why it doesn't work. We can explain why it works or why it doesn't work. Finally, we show some closed loop control design. And in particular, I would say tactile sensor is a key technology to reason contact state. If you don't estimate, if you cannot measure, how can you control the system, right? So of course, you can use joint encoders or four-stroke sensors to estimate contact state. But I would say at least for this project, visual tactile sensors such as gel stream, gel sight would be key technology, which can provide very, very contact-rich information. Okay. Of course, there are many challenges, especially for my manipulation task. I always consider contact mechanics in 2D. But of course, ideally, we want to consider 3D contact mechanics. But the challenge is, in 3D contact mechanics, now you need to consider, for example, first, if you can see my camera for people who are attending Zoom, but we're gonna first have like this kind of like patch contact, and now you're gonna have this kind of line contact, and eventually you're gonna have point contact. So you need to reason this kind of change of contact, which is quite challenging if we want to do in model-based optimization. also I assume that object is not deformable, but of course, considering deformable object would be very, promising direction. In the linear dynamics, we have the very great theory, right? Controllability and observability. For this kind of non-smooth contact dynamics, we cannot have this kind of theory. I mean, as far as I know. And I think working on this kind of field is critically important because when I actually, okay, let me use this one as an example. For tool manipulation, I cannot identify what's the good tool orientation at t equals 0. If I can understand the controllability, or if with this orientation, robot can do control, or if this orientation, robot cannot do control, I want to understand this kind of stuff. And it would be cool if we can understand this kind of theory for non-smooth contact-rich system. Okay. And also nowadays, reinforcement learning or machine learning has shown impressive results. For example, like reinforcement learning algorithm from Marco Hatter's group at ETH has shown impressive results. Because we have very good model-based optimization techniques, maybe we can utilize our model-based optimization to like warm start like learning skills so that we can achieve more robust tasks for locomotion and manipulation. Okay, so that's pretty much it. So I would like to conclude this presentation by saying thank you to everyone. Especially I would like to say thank you to, Professor Dennis Hong. He's my advisor. He has been my advisor over the last 5 years. And he's very great. He gives me all the feedback. He also gives me some feedback in like my career, non-research stuff also. So that's very appreciated. Thanks to him, I could enjoy my fun, but sometimes tough PhD journey. So I really appreciate his like kind feedback and great personality. Okay, and of course, I would like to say thank you to all the committee members, Professor Vandenberg, Professor Decomposition, and Professor Lopez, and Professor Santos is also here. So thanks for coming. I really appreciate, and I'm very honored to have you guys because you guys are expert in like optimization, robotics, planning, control. So I'm very happy. And during my PhD, I was very fortunate to have internship positions at MAR, Mitsubishi Electrical Research Lab, and BDAI. I want to say thank you to Pan, JW from BDAI, and Devesh, Arvin, Diego from MAR. In particular, I would like to say thank you to Devesh, Arvin, and Diego, because some manipulation work I presented during my presentations, a collaboration with MAR. So I really appreciate with their kind feedback and like infinity passion on the manipulation. Okay. And I want to say thank you to Space Robotics Lab from Tohoku University. I have been working on free climbing projects since 2016 when I was third year undergrad. And they are the people who helped me how to do research. And of course, I want to say thank you to all the Romera students. I had very great, amazing, chat, discussion, non-research stuff, some research stuff, engineering stuff. I really appreciate it. Especially I want to say thank you to Shen, Yusuke, and Alex. Especially I want to say thank you to Shen because he's a guy who helped me a lot, especially first few years. I didn't know all the research stuff, but he's a guy who stayed pretty late night, like 1 a.m., 2 a.m. together with me to debug all the code. He's a guy who helped me like all the like open problem. So I'm very fortunate to work with such a like great mentor and optimization expert. So, and of course, Yusuke is great. He's the next level in like both software and hardware. Thanks to him, I could work on like the great like robotic hardware experiments using Sylvia with gripper and scaler. So that's very great, and I was very happy and fortunate to work with him. And last but not least, so Alex, and I had great collaboration with him. I could do many interesting work. For example, the climbing task I did, that one was of course Shen and Yusuke also helped, but we use Alex force controller to do some force feedback. So that's very appreciated. And we did internship at MAR together for 2 summers. So we had a very good chat, not only research, but also non-research stuff. So I really appreciate his kindness. And all the, robots, friends, family. We did some demo in IROS 22 in Kyoto. This was crazy moment because we wanted to bring the robot to Japan. And unfortunately or fortunately, we have to bring the environment to the Japan. But as you can see, because our wall is too huge, it gets stuck with the hotel. So it was very, I don't know, challenging moment, but very contact rich. But eventually we could do some live demo. So that was a great moment. And that's it. Thanks so much for your time. Yeah.
All right, great presentation, Yuki. Thank you very much. So again, I'm not sure if the audience can hear me, but at this point, I would like to open it up to the audience if you have any questions. Or Yuki, since I cannot see who's there, you pick the question
Okay. Yeah.
from the audience.
Yeah.
Oh, by the way, Yuki, if
Yep.
you could turn off the sound for the video so I can hear.
Okay.
Yeah.
Oh shoot. Okay. Let me share my screen again. Share screen presentation. Okay. Thanks. Yeah. Okay.
So first one is when you say normalize the time,
Oh. Okay.
phase. So when you do that, does the optimizer still estimate or make predictions of when the happens?
In the context, so we assume.
Yuki, for the Zoom people, we cannot hear the question. If you can very briefly restate the question for us, that would be great.
I see. So Shen just asked the question about if the optimizer knows contact.
Yes, we do this, right? So like the contacts change.
Yeah.
So you do MPC for stuff, so you do make predictions when is next contact.
Yeah.
So when you normalize, does the MPC or the controller still do that?
Yeah. So Shen asked the question about if our framework thinks the prediction of the contact location, especially in MPC setting. So first of all, we did just planning, right? So for this planning, we can assume that contact location does not change during manipulation. So we didn't do such a prediction. But yeah, I think that's a great point. I think if we want to do, of course, MPC, right? As I mentioned in the closed loop control part, we need to do some estimation. So I think if we want to do this kind of manipulation for MPC setting, I think we need to have such a module. Yeah. And you said you have another question. Yeah. Okay. Oh. Mm-hmm.
So I was wondering, like, principle times to become design estimator and server and control. So when you have the time more complicated, can you still cover or it has to be designed?
Oh yeah, so Shen asked very great question. So he asked, so in traditional like linear dynamical system, we can design controller and observer separately, but can we still like separately design control? We can still study controllability and observability decoupling or no? So that's a great point. I didn't think carefully, but intuition is, I would say, maybe no, right? Because contact location, as you maybe related to your first question, because we need to know because dynamics is now the function of the contact location, right? So in dynamics is characterized with the contact location, so it's kind of like looping. So I think in order to discuss controllability, I think we first need to estimate, or we first need to discuss maybe observability, and in order to discuss observability, maybe we first need to understand controllability. So this kind of chicken and egg problem, I don't know, but that's my intuition. Yeah. Okay. Okay. I think I have a question from Kentaro Uno. Go ahead.
Hello, Yuki, and this is Kentaro Uno speaking from Tohoku University Space Robotics Lab. I'm sorry, I'm reluctant to turn on my video. Here in Japan, this is early morning. I still put in my PJ, so I'm sorry for
Thanks.
that. I have a very simple technical question. Thank you very much for your very interesting talk. And I'm not familiar with the visual tactile sensing tool. That is a gel, I guess. So where actually this gel is implemented in your test bench, and what parameters does the tool is measuring?
I see. So we did not manufacture in our lab. So we basically, so this is a collaboration when I was doing internship at MAR, Mitsubishi Electrical Research Lab, where I think MAR has been doing collaboration with like Professor Alberto Rodriguez group at MIT, where they manufacture this kind of gel stream. So I don't know super technical detail about like the parameter of the gel stream, but we use like very similar gel stream during manipulation. I don't know if I'm answering your question. What's your question again? Maybe.
So which part does this gel is implemented in your
I see.
last video test bench?
Yeah. So it is attached to the finger chip of the robot finger.
I see,
So,
and then it can measure the deformation of the gel so that the robot can estimate the torque at that joint.
So yeah, that's a good point. So actually, we have some. I was very rushed. I did not explain so much detail. So what we did was, so we basically, so each gel is covered with like black markers, and we can estimate how much markers moves. And using this information, we did some like polynomial curve fitting. So I would say the simplest way to do some machine learning or like some system identification. So we basically get optical flow. So it does not give you any torque, but I know some papers from Alberto's group, they did some estimation of how much torque is happening from this velocity field. For this project, we did the simplest stuff. So just we measure how much each black marker moves, and we check how much the ground truth is moving, rotating, and we did some polynomial fitting.
So in this experiment, you are using this tool to measure the how much angle is rotated at this joint.
Exactly. We want to estimate how much tool rotates with respect to gripper. Yeah.
With respect to gripper. I mean, is it possible to use the very simple angular encoder instead of this gel?
I see. I think that's a good point. I think for this specific task, yeah, maybe you can use such a sensor to estimate the relative angle. I think we did not use full potential of this gel stream for this tool manipulation. I think gel stream, as you can see, this is, yeah. So this is, I mean, we can do many things, right? We can also potentially estimate torque. We can also estimate how does contact patch looks like. We didn't actually fully utilize all the potential of this sensor. But yes, for this specific purpose, yeah, maybe we can do something like that. Maybe just using encoder might be okay.
Okay, I understood. Thank you.
Yeah, I think so. Yeah. Okay, yeah. Thanks, Professor Santos. Yeah. Slide 83. Okay. It is.
I like your approach to developing a framework for object agnostic.
Thanks so much.
So a couple questions about what you're controlling. Are you controlling the grip force at all, or just observing what the Nielsen tells you about relative orientation between tool and effect?
I see. So Professor Santos asked the question, how does the control look like for tool manipulation? And yes, actually, for grasping force, for normal force, I use exactly same force during manipulation. But I still, for stiffness control, I still command force on this plane. So that's the.
So you in the pivot plane?
Exactly. Yeah. So I mean, actually, not directly, but I still control the contact force at fingertip, not tool chip, but on this pivoting plane. Yeah.
And I noticed that there's sandpaper between the object and the support surface, and there's tape between the tooltip and the object. So are you controlling the kinematics of the tooltip, or are you actually producing, are you inferring a force at the tip of that?
Yeah, so we actually running stiffness controller at the end effector of the robot finger. And because we know tool geometry, we can propagate contact force from fingertip to tool chip. So we can kind of indirectly doing stiffness control also at tool chip. So we are doing not only kinematics control, but also quasi-static force control at tool chip. I don't know if I'm answering. Yeah.
Your contact state between the end effector and the tool,
Yeah.
and inferring contact state between tooltip and the object, and then do you just assume something between the object and the surface?
Yeah, that's a good point. So actually in this work, we assume that object, the contact state between the object and the environment does not slip. That's one big assumption. Yeah, that's very important and critical input point here. Okay, yeah, Professor Lopez. Yeah.
About, I guess, the second part of your presentation.
Okay.
On the bus track compensation.
Okay,
Like these, I guess you go to slide 49 actually.
49, okay.
These margins sound a lot like invariant tubes that you find in like continuous time, like it's like tube-based MPC.
Mm-hmm.
Did you look at like the connections between what you're proposing and what it existed in terms of like tube MPC literature?
That's
like I'm curious to hear.
That's great point. So actually, I'm big fan of tube MPC framework. We actually wanted to do something like that. The key challenge is, I think, let me know if I'm wrong, but as far as I understand, in order to do tube MPC, we want to estimate like reachability of the dynamics, or we want to know, maybe no. And I think in order to formally discuss like reachability of the dynamics, I think for this kind of contact system, it's quite challenging. So that's why we didn't do that. But actually, when we did like first meeting among the collaborators, doing tube MPC was one of the most powerful candidates that I want to do in the future if I can somehow estimate the reachability.
But so then are you computing these margins? Is this like an output of the optimization?
Output of the optimization problem.
Okay.
Yeah. So that's the kind of interesting part. So we are not providing the margin to the optimization. It's not input, it's output of the stability margin. So this might be simple picture, but what we are saying that our approach, given nominal guess of the parameter, it can provide some upper bound, lower bound of the parameter. So in this case, I don't know. So how to say? Let's see. So using this kind of framework, we can design nominal trajectory with some margin. So yes, in that sense, it sounds like open loop tube MPC, but bounds are provided by framework as output.
Yeah, so you're probably not exactly computing a tube, but it sounds like part of the output of this optimization is something that squint at it starts to look like a tube in the sense that you get bounds on certain parameters that you know that your system will still perform within some margin.
Exactly. Yeah. Okay. Sounds good.
Questions with all this.
Okay. I think I have a question from Sang-Woon, I guess. Sang, go ahead.
Hi, Yuki. This is Sang-Woon. Thank you
Hi.
for great presentation. Yeah, I just have one question. So about the tactile tool manipulation,
Okay.
I was wondering if you didn't have the gel film or any other vision-based tactile sensor, how would you approach to the same problem without having tactile sensor? And from the answer that about the question, from that answer, what do you think is the advantage of using tactile sensor in this kind of problem?
I see. That's a great question. I know we can do many different ways, right? I mean, like your lab, we can potentially use instead of using visual tactile sensor, one other way would be maybe using 6-axis four-stroke sensor at the end effector, and using such a four-stroke sensors, we can potentially guess if the contact is sticking or slipping, this kind of information. Or maybe we can also potentially estimate parameter of the object, right? Such as mass or friction using complementarity constraints, stuff like that. So that's critically, I'm not saying visual tactile sensor is the only technology, but very good technology. And yes, as your question is very good because maybe if we can fuse visual tactile sensors such as gel stream and 4-stroke sensor measurement, maybe we can design much better estimator than what I just presented in this presentation. Regarding your second question, I think especially gel site would be very, very useful, in my opinion, to get kinematic information such as contact geometry or contact depth, contact shape, if the contact is sticking or slipping. I mean, okay, I said also using 4-stroke sensor, you can still estimate if the contact is sticking or slipping. But in my opinion, or in my limited experience, I think using gel stream or gel site can provide much more accurate, or it can detect much more small microscopic slipping. So if you want to do like some super like in-hand precise manipulation, I think using vision sensor would be very beneficial.
Yeah, that makes sense. Thanks for answering. When are you flying over to East Coast? Just wondering.
Sorry?
When are you flying over to East Coast? Just wondering.
When?
No worries. I can ask you offline. Yeah.
Okay, sorry.
Yeah.
Okay. So I think, Minkyo, I think you have question. You can use the action. I guess you can use it. Oh no. Okay. I don't know who has. Anybody who are having question about Zoom or? Maybe no. So if do you guys have any question in the room or?
Okay, since also due to time constraints, let's wrap it up for the questions from the general audience. So as you know, for PhD defense at this time, I will have to ask the audience to leave the room except for the committee members. So at this point, if you can leave, we're gonna have a closed room session now. So thank you very much for coming.
Yeah.
So Yuki,
Thanks.